Welcome back to our video module on statics. We've just covered the parallel axis theorem, and I'd like to introduce an idea to you. All right, so we took a look at this ruler, right? And when we took a look at this ruler, then we found the second moment of inertia, or the second moment of inertia, to see how well it resists bending. And then we looked at the parallel axis theorem, right? Where we said the moment of inertia about the centroid plus AD squared, plus the distance squared from the axis. I'd like to present to you a problem. What if we created some fictional object? All right, here's our axis. And we created a fictional object with the same area as this ruler, okay? Has the same area as the ruler. And it has the same moment of inertia. All right? So the area and the moment of inertia, they're the same. However, we're going to make a rub. We're going to say that this distance, this thickness of this object is really, really, really small. So small, in fact, that it's almost zero. Now, if this object right here is so small that its moment of inertia is zero, that means, look up the parallel axis theorem. Well, what's going to happen? I'm sorry. Back here I said that its overall second moment was I bar. That's not what I want. I want I. Here, let's erase that. It's just I. Okay. Now, if we make that distance really, really small, what's that going to happen when we integrate right here, y squared dA? This term right here, it's going to go to zero. All right? It's going to have hardly any, we're going to say an insignificant amount on its own, which means that in order for us to get an equivalent I and equivalent A, we need to move it off of this axis. And we're going to move it off of the centroidal axis some amount. We'll call it K. All right? And you can imagine we're going to keep moving this further and further away until we get far enough away that if I take A times K squared, I'm going to get the correct moment of inertia. So as a reminder, I'm finding some sort of shape, really, really, really small thickness. So that means that my moment of inertia around the centroidal axis goes to zero. And then I'm going to move it far enough away from my axis that I'm going to get the same moment of inertia. All right? This distance, when I do that, this distance is called the radius of gyration. And, some quick math will show you exactly what that is. We just write K equals square root of I over A. Sometimes we'll use this as a good measure, a good feel of how different shapes, how their moment of inertia compares. And we can even do that right now. We can get a little bit of a feel. Imagine two objects with the same area. All right? Two objects. They have the same area, but say one object, we could even use our ruler, right? Our ruler has the same, these two have the same area, right? But this blue one has a much higher moment of inertia. So we could compare the two by seeing that the radius of gyration of this object has a really high moment of inertia, same area, is going to be much larger than the radius of gyration of this object. So the blue one would be large and the green one would be small, a small radius of gyration. And you can kind of see how you could take like different shapes, different types of I-beams, different types of whatever the amount is, and by comparing the radius of gyration, it gives you a good feel of how the moment of inertia compares with the area. One final topic I'd like to cover here, simply because it doesn't fit in anywhere else, and that is the polar moment of inertia. Polar moment of inertia, it's just something good to see. Imagine you have a tube. tube goes like this. All right. And you want to know how well this tube resists not bending, but torsion. We're going to try and twist it. Now, if we try and twist it, its ability to resist twisting rather than bending is very similar, which shouldn't come as any surprise. A very similar equation is this. Polar moment of inertia, we take all sorts of really small shapes all the way around and we integrate r squared dA. One quick note is that this has to be the same cross section all the way down for it to work. And it doesn't need to necessarily be circular. It can be all sorts of weird shapes, but it is important that it's consistent all the way vertically. That is our polar moment of inertia. Thank you very much, and we'll get more on this topic on our next module.